Earth, our home. A blue marble suspended in the cosmic void, teeming with life in ways we once thought unique in the universe. For billions of years, we assumed our planet represented the pinnacle of habitability, the perfect template for life itself. But recent discoveries are challenging everything we thought we knew. Deep in research laboratories and astronomical observatories across the globe, scientists are reaching a startling conclusion. Earth might not actually be the best planet for life in our galaxy. This revolutionary concept is called superhabitability, and it's fundamentally changing how we search for life beyond our solar system. Consider Earth's vulnerabilities for a moment. Our Sun, while life-giving, is a relatively unstable G-type yellow dwarf that will consume our planet in approximately 5 billion years when it expands into a red giant. We cycle through devastating ice ages every 100,000 years, events that have driven countless species to extinction throughout our geological record. Massive asteroid impacts have repeatedly sterilized vast regions of our planet, with the Chicxulub impact 66 million years ago wiping out the dinosaurs and 75% of all species. Our magnetic field, essential for protecting life from deadly solar radiation, weakens periodically and has reversed hundreds of times throughout Earth's history. Volcanic supereruptions have triggered mass extinctions. Our axial tilt of 23.5 degrees creates extreme seasonal variations that stress ecosystems. Now imagine planets without these fundamental flaws. Worlds orbiting older, more stable stars that will shine steadily for tens of billions of years, giving life unimaginable time to evolve and flourish. Planets with thicker atmospheres providing superior protection from cosmic threats. Worlds with more stable climates that never experience catastrophic global freezing events. Based on decades of planetary science research, astrobiological studies, and sophisticated computer modeling, scientists have identified 4 specific categories of planets that could theoretically surpass Earth's habitability. The first are super-Earths, rocky planets with masses between 1.5 to 2 times Earth's mass. These larger worlds possess stronger gravitational fields, allowing them to maintain thicker, more protective atmospheres for billions of years longer than our planet can sustain. Their increased size generates more internal heat, driving robust plate tectonics and maintaining powerful magnetic fields that shield life from radiation. The greater surface area provides exponentially more diverse habitats, climates, and ecological niches where life can experiment with countless evolutionary pathways. If this exploration into worlds that might surpass our own home fascinates you, subscribe now and join us as we venture deeper into the cosmos. The second category of superhabitable worlds orbit K-dwarf stars, and understanding why requires us to look beyond our solar system's architecture. K-dwarfs are orange stars slightly cooler and smaller than our Sun, and this seemingly minor difference creates profound implications for life. These stars burn their nuclear fuel far more slowly, remaining stable on the main sequence for 20 to 70 billion years, compared to our Sun's 10 billion year lifespan. This extended stellar longevity provides life with 2 to 7 times longer to evolve from simple microbes to complex, intelligent civilizations. K-dwarfs emit significantly less harmful ultraviolet radiation than our Sun, reducing DNA damage and mutation rates in organisms exposed to their light. The habitable zones around these stars are closer to the parent star, yet remain stable for extraordinary lengths of time, creating ideal conditions for complex life to develop without the constant threat of stellar evolution disrupting the climate. The third type involves planets with precisely optimized water coverage, specifically between 80 to 90% of their surface compared to Earth's 71%. This isn't arbitrary. Computer models demonstrate that planets with greater ocean coverage experience superior climate regulation through massive ocean currents that distribute thermal energy evenly across the globe, eliminating the extreme temperature gradients that create devastating storms and climate instability on Earth. Larger oceans contain more dissolved minerals essential for life, supporting more abundant and diverse marine ecosystems that serve as the foundation for planetary food webs. The increased water volume provides greater reserves of hydrogen and oxygen, the fundamental building blocks of organic chemistry and biological processes. The fourth category consists of planets with average surface temperatures around 77 degrees Fahrenheit, approximately 18 degrees warmer than Earth's average of 59 degrees. This temperature difference might seem modest, but its effects on habitability are profound. Warmer worlds support dramatically higher biodiversity, because tropical and temperate conditions can exist across more of the planet's surface area, rather than being constrained by vast frozen polar regions that remain biologically inactive for most of Earth's history. Elevated temperatures accelerate metabolic rates and chemical reactions, potentially speeding up evolutionary processes and the development of complex multicellular organisms. Extended growing seasons allow more photosynthetic activity, producing more oxygen and supporting larger, more complex food chains from microscopic plankton to apex predators. These aren't merely theoretical constructs dreamed up by optimistic astrobiologists. Astronomers have already identified real exoplanet candidates that may possess these superhabitable characteristics, including Kepler-442b, Kepler-1649c, and others currently under intensive study.